Okay, is it recording? I don't even. Okay, it is recording. It is recording.
Yeah, pretty sure that's right.
Screen share? Oh, okay. I got you. I got you. Okay. All right. So we're talking about the logistic map, and this is the part two for the dynamics and chaos. I did a presentation on this topic last semester, and this is part two. And we'll be looking at the logistic map in detail. So here's the contents. Will first be, so logistic map is a family of functions and with this parameter mu. And this will be, we'll first be looking at mu between 0 and 3, and then we have some more other cases down below. Yeah, so let's look at mu between 0 and 3. This is probably the easiest case. So what's the definition? The definition of the logistic map is a function on the reals. It's actually a family of functions on the reals. And is equal to f of x is equal to mu x times 1 minus x, where mu is a real number. And then specifically, we will investigate mu greater than 0. If mu less than 0, then behavior is probably just the opposite, and it's like, no, it's like basically symmetric. And then, of course, 1D map is something defined like x sub n plus 1 is equal to f of x sub n. So you have start with some x sub 0, and then you have x sub 1 is equal to f of x sub 0, f of x sub 2 is equal to f of x sub 1, etc. Okay, so this is something from last time. So let's recall that a fixed point, x, is stable or attracting. Okay, first of all, fixed point is fixed point, and x is a fixed point if mu x is equal to x. Very simple. So a fixed point is stable if the absolute value of the derivative at this point is less than 1, and unstable if it's greater than 1. This is just something that was proved last time, but kind of what this means is that if you have a fixed point here and then you have like some function, everything around this in some interval around this fixed point ultimately goes to this fixed point after many iterations. So bifurcations usually occur at the marginal stable point, where the absolute value of derivative is equal to 1. So bifurcation is defined as the okay. We'll talk about bifurcation in another section, but for now we don't need to worry about this because for mu in the range 0 to 3, there's no bifurcation. But we'll see what that means. So initial fixed points for small mu are given solutions to the equation x equals mu x times 1 minus x, which is just this equation right here. And then we can solve for this, and then we obtain that the fixed point is either 0 or 1 minus 1 over mu, right? And then we can take the derivative, c, and then we can see that 0 is stable for mu in 0 to 1, and 1 minus 1 over mu is stable for 1 to 3. Okay, also feel free to stop me if there are any questions. Since there's only 2 people, I can answer many questions. Time to give up on the work. So this is the first and immediate result we have. So if mu is greater than 1, then if x less than 0 or x greater than 1, then the orbit of x eventually goes to negative infinity. So what this means, actually the working marker, right? So the function kind of looks something like, so we have f of mu x 1. The function looks like this, right? So what this looks like is that this is 0, this is 1, and the function looks something like this. As an upside down problem, right? And then what this means is that basically, if you are to the right of this point, or to the left of this point, so greater than 1 or less than 0, then eventually the orbit of x goes to negative infinity. So this is very obvious because, so first we can see that if x is greater than 1, then f of x is less than 0, which reduces to the x less than 0 case. So now let's focus on x less than 0. So note that x when x is less than 0, then x is always greater than f of x. What this means is that if you look at this is y equals x, then the graph here will be always below this line, right? Yeah. So then this sequence, so f of n, f to the n of x forms a decreasing sequence. And then we can so this shows that it's always gonna be less than 0. But now let's show that this sequence cannot converge. If we show this, then we will obtain that the limit of x to the n of x goes negative. Now suppose that it converges, suppose by contradiction that it converges from P. Then you can construct another sequence, f to the n plus 1 of x. Because the f to the n converges to P, then f to the n plus 1 also will converge to P. But by the continuity of f, we have that f to the n plus 1 of x converges to f of P, which is less than P. And this is a contradiction. Okay. Any questions so far? All right, let's continue. So this is another result here. And this basically gives us the notion, this demonstrates the notion of the tracking fixed point. So if x is between 0 and 1, so last proposition was for x less than 0 or x greater than 1. But now let's consider x in between 0 and 1. Then the orbit of x will converge to the fixed point, which will converge to the tracking fixed point, which for let me move this thing at the top. Yeah, which for mu in between 1 and 3 will be 1 minus 1 over mu. So how do you show this? Let's split into two cases. And actually, you need one. It'll be very hard. Yeah, we could do that, but I want to draw something. Okay, let's follow that. So wait, should we follow that? Okay, that's not a good idea. Oh, wait, I didn't bring it. So sad. Okay, let's split into two cases. Mu is between 1 and 2. Mu is equal to, well, three cases actually. Mu between 1 and 2, mu is equal to 2, or mu between 10. So first of all, we can check for mu equals to 2, just explicitly. And for mu between 1 and 2, we have that the fixed point is, yeah, it actually the fucking draw. So sad. You guys like see this thing? Or like you can kind of like move up it. Yeah. Like basically for mu less than, yeah, wait, I can actually doesn't want this. This is, I think it'll be pretty easy. Huh? No, this is like I want to. All right. Okay, you guys see this. So you can see that if, for example, for the mu less than, mu is 8 in this case, for mu less than, for mu in between 1 and 2, basically the fixed point here, right? This is the fixed point because it's the intersection with the line and y-axis. The fixed point will be less than 0.5.
Yeah.
And how the proof goes is that if you're in this region, like the fixed point is here, right? So maybe somewhere here. If you're in this region, then f of x will be greater than x. So you'll get continuously mapped up to some value larger.
Yeah.
Right. So for this region, it'll converge. And then for between this and this, between the fixed point and 1/2, 0.5, this will be, we'll map to something that's smaller. We'll map to something that's smaller than x. So it'll converge this. It'll converge to the left. I mean, it will converge to something, so f of x will always be less than x. So it will like continuously decreasing until it hits this point. And then on the other side, you can like symmetrically draw another line here where you reflect this point across. X equals 1/2. And then for everything to the right of this, one iteration will map to here. And then for everything in here, one iteration will map to here. So the right-hand side, after one iteration, the right-hand side completely maps to the left-hand side, and we can just use the same result.
Okay.
Okay. Yeah, so this is something that's more formal, I guess. Yes, so key point is that like 1/2 to 1 gets mapped to 0 and 1/2. And then, okay, so the other case is mu between 2 and 3. So in this case, the fixed point will be greater than 1/2. It'll be like up here. Okay, big flag. Big. Yeah, so I mean, this is like kind of the same already. So we can define the another point here where you reflect this across x equals 1/2, and then which will be some point here, right? And then, so for everything, of course, for everything greater than this point, we have that f of x is less than. So you like maps something small. And then the argument this here is like you need a more specific argument, because if you consider the mirror point here, everything left of this gets mapped up to something, but that something does not exceed this. But inside the mirror point to the middle, you map up to something greater than this. And you can show that if you map something to greater than this, you end up like somewhere here, and then which will be mapped back to somewhere here. So you need to do some work. You need to do some analysis with f squared, which is kind of shown here. Yeah, so you can show that like you can basically show that if you take x squared, so this will be mapped to the left-hand side, and then we have the same result. I mean, all this is not very interesting. This is just a very simple case that you can probably just observe right away. And then for mu between 0 and 1, the results are similar, but now the attracting fixed point is at 0, and the 1 minus 1 over mu will be repelling, and that thing will be less than 0. So it's like Go back to dense mode. So I guess right, you see this point, is the other fixed point that's not at 0 is not down here. So basically you can follow the same argument. Everything greater than 1 or less than 0 gets mapped to infinity, and then between here and here, you get mapped f of x is greater than x, so you get mapped to order. And for here, everything in this range, everything f of x will be less than x, so it gets mapped to something else. Yeah, so this is kind of just like by the same reasoning as mu between 1 and 3. So does that make sense? Like basically, like the key takeaway here, what attracting fixed points. So like here, 0 is attracting fixed points. So everything, I guess everything from between here and here ultimately gets mapped to 0. So it's like some neighborhood where it's like all the orbit converges to the attracting fixed point. Let's just keep it like this for now. Okay. Okay, so this is for mu greater than 3. So this is what the rest of the talk will be about. So we have pure doubling until like this value, which we'll see where that comes. And then, so I'll cover mu up to that value, like 3.55699 something. And I'll also cover mu greater than 4. But for mu in between these two, it is not very clear what's going on. And I guess people are still researching. And then mostly it is chaotic. We'll see what that means. And then it's also local ranges where it's non-chaotic and it's like whatever. Okay, so now we look at bifurcation. By the way, mu infinity is just that like 3.59 something that we saw earlier. So what is a bifurcation? A bifurcation, so lambda is an external parameter. So in our case, this is mu. And let f be a function that's dependent on lambda. So it's a family of functions on lambda. And yeah, so varying lambda gives a family of functions. As we change f by varying lambda, there are certain points in the family where the qualitative behavior of the function changes. So the points of lambda where this change occurs is called a bifurcation. So let's see a specific example of a bifurcation that is called a pure doubling bifurcation. So what this means is that originally you have an attracting fixed point somewhere. And then at this point, at this value of lambda, this now splits into two. But this now splits into two attracting fixed points of period 2. So what that means is that f squared of x is equal to x, as opposed to f of x is equal to x. And there's some other restrictions. Maybe you see that, oh, the original one is still a fixed point, but now it's repelling, and then it's like you have some uniqueness or whatever. Is this definition clear?
What is cycles of period 2?
Right. So a cycle. So basically we have that f of q1 is equal to q2, and f of q2 is equal to q1. So basically we have f squared of q1 equal to q1, and f squared of q2 equal to q2. So these 2 points that now come into existence are periodic points of period 2. Does that make sense?
Periodic.
Yes. So a periodic point of period n is a point such that f to the n of x is equal to x.
Oh, okay.
Yeah. So basically, again, f q1 equal to q2 and q2 equal to q1. Okay. Right. So at mu equals 3, we have that this is a marginally fixed point, which is because the absolute value of the derivative is equal to 1. And there is some theorem that gives sufficient conditions for pure doubling bifurcations, and you can see that it's like satisfies the theorem. It's like not very interesting, like, but this is basically usually the bifurcation occurs at where absolute value derivative equals one. At least for this map, right? And then we can solve for the periodic points after the bifurcation because they're just x equals f squared of x, just a quartic equation. You can factor out the initial fixed points because there's so many fixed points in this equation, and then you can get the other 2 points. It's very simple. I mean, this is just making computation. Okay, and then you can, for a subsequent period doubling, you can basically do the same idea, except you now use chain rule. And then, for example, if you go from 2 to the n minus 1 to period 2 to the n, then we use the fact that f of 2 to the n minus 1 will have derivative of -1, which is just a pattern. And then we can chain rule this, expand it out, and then yeah, we have, so basically it's like if we have all the previous fixed points or previous fixed points for the lower period, then we can solve the function, solve the equation.
Wait, is -1 a constant? Like, why can't it be 1? It's the only condition before it said.
Right, so this has to do with the theorem about period developing bifurcation, which I choose not to do that. But if you look at
just like some random lower.
Yes, just some random lower. Yes. All right, and then so you might wonder what happens when you keep going. What happens when period doubling bifurcations happen over and over again? So we have initially you have period 1, which is the big point, and have period 2, period 4, period 8, period 16, etc. Like what happens? Like what happens in association? So it turns out that for all 1D maps with a single local production, which is our case here, obviously, because it's just a upside down problem. We have a local, we have a single locally production. The max, sorry. Turns out that for these maps, the ratio between the consecutive bifurcation points approach a term called the volume of constant. So how this is defined? So let Qn be the value of the nth bifurcation. Nth mu where the bifurcation occurs. Then that's the delta n be basically the previous gap between the previous gap between bifurcation points and a new gap. This is like this ratio here. And then we take the Python constant is basically the limit as n goes to infinity of delta n. So this is experimentally seen to be maybe 1.669 something. And then as expected from geometric series, Qn will convert. So Qn, we call it that the value of Q for nth bifurcation. So which is mu in our case. And then we can denote the limit as Q infinity. And then this is some constant value, which we saw earlier as 3.5699 something. So for mu less than this value, we have increasingly close together bifurcation, like bifurcations with decreasing space between each one. And then eventually near this point, we have like maybe unbounded number of bifurcations. Might help to show a graph of what this looks like. Yeah, let's look at that. So basically, if you just look at this, I mean, it's just qualitative. It doesn't really matter what the actual parameters are. You initially have like just one fixed point, and then branches off into two periodic points at period 2, and then it branches off to period 4, and then period 8 here, and then quickly becomes very dense. Or something like this. And of course, the x-axis will be the value of the parameter v, and y-axis is the value of the periodic points. So what I mean, quantitatively, you just look at x-axis, and you see that as you increase it, you have many bifurcations. Okay. Let's actually skip this. We'll come back later if we have time. But it's hard to explain without actually drawing something. Okay, now let's look at symbolic dynamics. And this is our approach. This will be our approach for mu greater than 4. We'll use this standard technique to easily solve for mu greater than 4. Right. So we introduced this alternative metric space of sigma 2. So previously we were working the metric space of R. Now let's forget about that for a second and consider this metric. So sigma 2 is defined as the set of object strings of, I mean, for infinite links or like links of n where n is in natural numbers. I just maybe it's not completely rigorous, but you know what I mean. And then we can define the metric as this thing here. So distance between two elements s and t in sigma squared is just the sum over the pairwise differences and over 2 to the I. Maybe you can think of this as a decimal number in base 2, something like that. And then, but you take the absolute value here. And then proposition D is a metric, very easily checked. And then this is a critical observation. So if we have two terms, we have two elements in sigma 2, s and t. If the first n terms or the zeros index to the nth index all agree, right? Then the distance between them is bounded by 2 to negative. And as you can easily check this by just taking geometric series on the n plus 1's term to infinity. And otherwise, on the contrary, if the distance is less than 2 to negative n, then the zeros to n's index will all agree. This is very critical for later on when we try to bound this distance by some epsilon, and then we can always take some. So we can automatically know that for some n, the first n bits will agree. So is this definition of sigma 2 clear? Yeah. Right. So let's define a function on the shift map denoted lowercase sigma. Basically, if the original sequence is like 0, 1, S0, S1, S2, and then you shift it, basically it cuts off the first one, then you're left with S1, S2, S3. Just then you shift towards the left, and the leftmost bit gets deleted. And then we have a proposition, so sigma is continuous. Well, do you want me to prove this? I think this is pretty straightforward. So maybe you just take again, like we can look at the previous slide and we can use the second observation here. So if the distance is less than some epsilon, then there exists some n where the first n bits are equal. Gosh, I cannot write. So basically, like you can type this by just using straightforward epsilon delta. Not very complicated. Like you end up with something like you just take Like, for example, you have epsilon and then the first m bits agree, and then you just take something where the first m plus 1 bits agree, and it's like within the epsilon. Well, let's look at some properties of the map. See, we have a proposition. One, number of periodic points of period n is 2n. Two periodic points are dense is sigma 2, and three there exists dense orbits. So immediately we can see that sigma 2 is chaotic. So recall the definition of a chaotic map over a metric space is that one, the periodic points are dense, and two, that there exists dense orbits. So we automatically see that if we prove the proposition, we immediately see that sigma is chaotic. I mean, yeah, sigma is chaotic the shift map is chaotic in sigma 2. So now let's think about how to prove this. Very easily done. So a periodic point of period n, obviously, is in the form of something like this. So maybe S0 dot 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 S n minus 1. And it repeats again. It repeats itself. S0 to n minus 1, S0 to n minus 1, etc. Right. And then, so a period n, how many such periodic points are there? Well, that's just the number of unique bit strings S0 to S1, Sn minus 1. So that will be 2n such periodic. It is clear.
It's kind of confusing for the form of a periodic point.
Yes, because a periodic point n is that the shift map applied n times. So sigma to the n of S will be equal to S.
Oh,
so what does that mean? So after you apply sigma once, you're left with S1 to S1, n minus 1, S0 to n minus 1, etc.
Okay.
So then after that, if you apply it n times, this prefix gets deleted. So you're back to where you started. So there are two ends of periodic. And then the second thing we want to prove is that the periodic points are dense. Why is that? We use so definition of dense is that for all points in sigma 2, we will have a period. For all points in sigma 2 and for all epsilon neighborhoods of this point, we will have a periodic point inside this epsilon. So we will again use the critical observation made earlier. So let's take the epsilon. And that means that for all points inside this epsilon neighborhood, we will have S1 equal to T, Si equal to Ti. So the first some m bits will agree, right? And then you simply just take this. Because this is a periodic point, and this guarantees that you're inside the epsilon neighborhood. Third thing is that there exists a dense orbit in sigma 2. So a dense orbit is an orbit of some point that goes arbitrarily close to any other point inside that goes arbitrarily close to any other point inside the metric space. So this will be the formal definition. There exists some S such that for all t epsilon greater than 0, there's going to be some iteration that goes arbitrarily close to t. So what this means is that again we use the critical observation. Is that this distance less than epsilon will mean that the first m bits agree for some m. And then let Sm to be the concatenation of an enumeration of all bit strings of linked m. So what does this mean? This means that if you have some m, and then you have an enumeration of all the bit strings of linked m. So maybe you have all zeros, and then 0, 0, 1, 0, 0, 0, 1, 0, something like that. So maybe for m equals 2, you have 0, 0, 0, 1, 1, 0, 1, 1, and then you just take a concatenation. That's something enumeration. And this is always countable because it's a Finite number. And then you take S to be the concatenation of all these SMs for M in that. So this means is that let's say you have this, and then you have and now front you have 0. Holy shit. 0, I'll probably have 0, 1. And then you have zeros. Okay, and then you have 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. And it's basically, you can pick any point. And you can pick some epsilon. So you will have, the first n bits will agree. And then you can just take, for example, maybe you take 1, 0, 1, 0, 1. Yeah, like you see what I'm going with this, right? You take 1, 0, 1, and then maybe you want the first 2 bits to agree. Then you go here, go here, go here, and then go here. And then this is what you want, right? Because if you have this, you have the point, if t is equal to 1, 0, maybe 1, 1, 1, 1, 1, etc. And then you want to go within two bits accuracy. Then you can just go here. Similarly, if you want 3 bits accuracy, you can just go to 1, 0, 1, wherever that is in the. It is clear. Okay. Sounds good. Right. So now we're going to now we try to relate this sigma 2 metric space to, and it's a sigma 2 metric space and the shift map over the sigma 2 to our logistic map over R. And by doing this, by doing some magic, which I will describe right now, we will have that the logistic map is also chaotic. Because earlier we showed that sigma is actually chaotic on sigma 2. Shift map is chaotic on sigma 2. So we can try to make some analogy with the logistic map over R, from which we will obtain by this analogy that the logistic map is chaotic on R. So first, we need to define a set called capital lambda. And this thing is defined as follows. We take AN to be the set in 0, 1. Well, obviously, because, well, yeah, let's actually see what this means. So take X to be in 0, 1, and Fn is in 0, 1, but Fn plus 1 is not in 0, 1. So what this means, if you consider this graph again, I don't want to draw it. Mark is more every time I draw. So maybe A1 will be the pointing here, and then for pointing here, I mean, let's assume that let's assume that this thing does not exceed 1. Then this will be the pointing here, and then F2 will be right. Let's have a look at that close. Tired of this crap. So F2 will be something like this, right? Like I have 2 peaks, kind of thing. And then you can also show that. Yeah, hang on. Right. I think this illustrates the item pretty well. So for black line on top is actually white. And then for this interval, you kind of see how the red line, which is just F, goes above 0, 1. So what happens when it goes above 0, 1? Then on the next iteration, then it will be mapped to somewhere outside here, right? It will be mapped to somewhere outside to the right of 1. And then on the next iteration, it will immediately become negative, and then it will go here, and then it will just merge. It will just go to negativity. So essentially, we're trying to construct a set where all points in the set will always stay in 0, 1, no matter how many iterations. So for example, A1 will be this set and this set. Middle one gets mapped out and gets deleted. A2 will be maybe here, here, and here, and here. Because you see at the top, the purple one goes above 1. The purple line goes above 1, and then we want to delete the intervals in X where this happens. And then, of course, you can take, maybe just to illustrate, we have, right, so again, all those little things at the top, corresponding intervals, we don't want that. So we delete them. That'll actually be a to the a sub 3, I guess. Well, I mean, yeah, I mean, this is actually made, let's do, yeah, this will be a sub 3. And then we do this for all n. And then what's left is our set length. So this makes sense. So basically, we want to construct a set where all points in the set will always remain in 0, 1, no matter how many iterations you take. And we want this because when it goes outside 0, 1, then it will just go to negative. And then this is actually a Cantor set. Lambda is actually a Cantor set. A set S is a Cantor set if it is closed, totally disconnected, and perfect. So totally disconnected means there is no intervals as connected subsets. And perfect means every point in S is an accumulation of all other points in S. An accumulation, so the perfect means is that for all points in S and for all epsilon neighborhoods of that point, there exists another point in S in some epsilon, in that epsilon neighborhood. And then we can prove that, wait, maybe this is 2 plus 5. You can prove that for lambda greater than some quantity, for mu greater than some quantity, the set lambda is a Cantor set. Proof is, let's skip this. Let's skip this and come back because we're only here until 6 o'clock. Right, so I mean, I guess this doesn't matter that much. We'll see if this matters. Like actual. Maybe just random. Now this is critical here. So a function, so let's recall the definition of a homeomorphism. A homeomorphism between two metric spaces X, Y is a continuous bijection with a continuous inverse. And suppose we have two metric spaces X and Y, and then we have a function from X to X and from Y to Y. So a function F from X to X, function G from Y to Y. Then F and G are topologically conjugate. If there is this homomorphism X from X to Y, from H from X to Y, such that H composed F is equal to G composed H. So what does this mean is that, please mark, let's, so you consider this diagram. X to X, take F. Y to Y, take G. And then from X to Y, you have this homomorphism H. So basically, this path gives you the same result as this path. This makes sense. This is a commutative diagram. So basically, and also H is a bijection. So I guess if you take F, then going around this way, get you back just the F. So we can define the following function from lambda to sigma squared. And we can prove that this function is a homomorphism. So this is probably the hardest part, proving it's a homomorphism. So let's look at what this function does. So the domain is lambda. So yeah, so the domain is lambda, so this will be X in lambda. And then we can say that the function S of X will be an element in sigma 2 And of course, this will be a bit string. And then the ith element of this bit string will be equal to 0 if f to the I of x is in I naught, and it will be equal to 1 if f of I of x is in I1. Where I is this, and where I naught is this, and I1 is that. So what are these two sets? Let's go back to Desmos. And let's get rid of all this crap. Yes. So I naught will be from here to the 0.34, for instance. So this will be so in the middle it's mapped out to, it's mapped out of 0.1. And this is to the left. So I naught will be the interval to the left where it stays in 1. And I1 will be the interval to the right where it also stays in 1. So yeah, we can define this function. And then this turns out this is actually a homomorphism that we want to establish topological conjugacy between set lambda and sigma square. So it's the definition of a function. Okay. So let's first prove continuity of that. Yes, so we will use the sequential criteria. Let's consider an arbitrary sequence in the converges to x. Then we want that S of xn also converges to S of x. So that means is that for all n lambda greater than 0, there's this n such that all small n greater than n, you have the distance between these two is less than sigma. And again, we use the critical observation that these two guys has distance less than epsilon, means that there exists some m where these two guys, the first m bits of these two guys agree, right? Yeah, I even said take m such that 2 to the minus m is less than epsilon. So what this means is that for all I less than or for all I less than m, the ith iterate of f applied on xn and x agree on whether they are in 0, 1, or whether they're in 0 naught, I naught or I1. Does that make sense? By the definition of S, all these iterates of order less than or equal to m agree on whether they are in I naught or I. So let Ji be the interval that they are in. They are both in. Let's just call this Ji. Then for each I in the string, let us pick because fi is continuous. Yes. Wait. Yes, because fi is continuous, we can pick some epsilon I such that these two things, again from above, agree on the interval. Yes. So after that, we can essentially, because by continuity of, wait, hang on, this is actually a big count. Yeah, so yeah, I mean, like basically you can take epsilon I, which is like the distance between these two. And then by continuity of f to the I, we have that there exists some delta I, such that for all y in this delta I neighborhood of x, we have that the ith iterate of f, the distance between these two is less than epsilon 1. And then we simply take delta be the minimum of these delta i's. And we're taking a minimum over a finite number of deltas, so this makes sense.
Quick question.
Yes.
Why is it always possible to pick some epsilon I group such that Fi mu xn and Fi mu x group? Oh, because Fi is continuous?
Oh wait, sorry, what's the point?
Why is it always possible to select this epsilon? Is it because F raised to I is continuous?
No, it's actually because like it's just that because like you're on the interval somewhere. Like you're on, for example, you're on JI somewhere.
Wait, who is you?
Oh, sorry. Oh, I'm so sorry. This so this thing isn't. So consider fi of x, right? F to the I of x, and then that's gonna be on the interval somewhere. Like it's gonna be on ji somewhere, right?
Yeah.
And then we can take some epsilon such that. Fucking, I want to draw. For example, you're on ji,
Yeah.
and then it's like suppose you're here.
Yeah.
Then you can take some epsilon equal to around that, so that all the points inside here will also be in this ji.
Sure.
This is the epsilon. This is the epsilon there.
Sure.
This is the epsilon we're constructing.
But okay, wait. But this epsilon also requires that Fi x to the n is also in Ji, right?
But it's just for f raised to I.
Wait, what? Oh. So how do you enforce the restriction that Fixn and Fix agree on?
Oh, do you guys have a meeting?
We have this room for six.
Okay, well, anyway, we have many hours to discuss this.
Unfortunate time. Wait, proof